Hello, my name is Zach Knoll and I'm a member of the Atrium Cardiology Collaborative. I'm looking forward to talking today about antiplatelet drugs in what is the first of several videos titled #Back to the Basics. The intent of these videos is to provide a brief physiology and pathophysiology primer and then focus in on the mechanisms of action of medications as it relates to these disease states. Today our video will briefly review primary hemostasis, which consists of platelet adhesion, activation, and aggregation, and identify where and how antiplatelet medications work along this process. To start things off, let's briefly go over platelet physiology. As you may recall, platelets are produced in the bone marrow and originate from megakaryocytes. Platelets are unique in that they're essentially specialized cell fragments that contain no nucleus. During their inactive state, they are lens-shaped as shown on the left side of this picture, and once activated undergo a conformational change, as depicted on the right side. Platelets have a lifespan of approximately 7 to 10 days and contain key organelles that are referred to as granules or bodies, which are responsible for releasing potent clotting mediators once activated, ultimately leading to the primary function platelets serve, hemostasis. Hemostasis, or the process of stopping blood flow, consists of primary and secondary phases. Primary hemostasis is the development of a platelet plug, and secondary hemostasis refers to the development of a fibrin-rich meshwork created to stabilize the platelet plug. Antiplatelet drugs work predominantly during primary hemostasis, and thus will be the focus of the remainder of our discussion. When you think about primary hemostasis, I encourage you to think of it in terms of a three-step process, or the 3 A's. The first of these steps is adhesion. As depicted in the first picture, when injury occurs within a vessel or tissue, inactivated platelets come in contact with the damaged endothelium and adhere to it. This then causes the platelets to become activated, which is the second A in the process of primary hemostasis. You'll notice that the platelet undergoes a conformational change at this time. I like to refer to these platelets as angry platelets, because once they become angry, if you will, and release the contents of their alpha and dense granules, more and more platelets are recruited, amplifying the process and representing a classic example of a positive feedback loop. As more and more platelets are recruited and activated, the third and final step is for these platelets to cross-link with each other, or aggregate, so that a stronger, more stable platelet plug is formed around the site of injury. In terms of pharmacological therapy to interfere with this process, the majority of antiplatelet medications, such as aspirin and P2Y12 inhibitors, work in the activation phase of primary hemostasis. It's important to recognize that, although most antiplatelet medications work in the activation phase, they also have indirect downstream effects that decrease platelet aggregation by interfering with the positive feedback loop. Some drugs do exhibit their activity specifically in the aggregation phase of primary hemostasis, such as with glycoprotein 2B/3A inhibitors. Now that we've reviewed the process for primary hemostasis, let's focus in on the activation and aggregation phases and where our drug targets are. You'll see here a picture of a platelet with various receptors and biochemical processes that lead to platelet activation and aggregation. We're going to break this down into 4 quadrants and talk about each of the drug targets. Let's start in the upper left-hand quadrant and work our way through the picture of the platelet. The first drug target to discuss is the G-protein-coupled protease-activated receptors. These receptors are responsible for mediating platelet effects produced by thrombin. Now, typically we think of thrombin functioning to convert fibrinogen to fibrin, which makes up secondary hemostasis. However, thrombin is actually one of the most potent platelet agonists and thereby can dramatically influence platelet activation and aggregation. There are 2 key receptors whereby thrombin produces its effects on platelets, protease activator receptor 1 and 4. PAR1 has the greatest affinity for thrombin and thus is the target for Vorapaxar, the only US-approved PAR1 antagonist. Inhibiting PAR1 ultimately leads to reductions in amplification of platelet activation and indirectly reduces platelet aggregation. The next receptor we'll focus in on is the P2Y12 receptor. This receptor is activated by adenosine diphosphate, or ADP, which is released from dense granules during the platelet activation process. When ADP binds to P2Y12 receptors, intracellular cyclic AMP and calcium concentrations are increased. This ultimately produces greater amounts of dense granule secretions and increases expression of glycoprotein 2B/3A, leading to further platelet activation and aggregation, respectively. P2Y12 inhibitors ultimately reduce these downstream effects by blocking ADP from its receptor site. Next, let's look at the role of thromboxane A2, which is a potent platelet agonist and vasoconstrictor formed from arachidonic acid via cyclooxygenase 1. When thromboxane is produced within platelets, it ultimately binds externally to receptors on the surface of platelets, contributing to further platelet activation and amplification. Aspirin inhibits COX-1 and subsequently reduces thromboxane A2 production within platelets. Note that because platelets are not capable of regenerating COX-1 and because aspirin exhibits irreversible binding, COX-1 is inhibited for the lifetime of the platelet once aspirin binds to it. Also shown in this diagram is the role of phosphodiesterase and its effect on cyclic AMP and GMP. Cyclic AMP and GMP produce inhibitory effects on platelet activation. However, phosphodiesterase hydrolyzes these two chemical messengers, thereby increasing platelet activation. Phosphodiesterase inhibitors, such as cilostazol, ultimately reduce platelet activation by increasing concentrations of cyclic AMP. Lastly is the role of glycoprotein 2B3A. Glycoprotein 2B3A is a receptor found on platelets that is responsible for aggregation or cross-linking of platelets. Fibrin and von Willebrand's factor bind to glycoprotein 2B3A receptors between two platelets, forming a link between them and producing a more stable platelet plug. Inhibiting this with glycoprotein 2B3A antagonists, such as eptifibatide, directly blocks platelet aggregation and prevents the stabilization of a platelet plug. Now, after taking a look at the individual drug targets, let's take a look at the whole picture again. Hopefully by this point you've recognized that there is significant redundancy involved with platelet activation and that multiple receptors and chemical messengers are involved. In addition, I hope that you recognize altering upstream effects, such as with PAR1 receptor antagonists, P2Y12 receptor antagonists, COX-1 inhibitors, and phosphodiesterase inhibitors, ultimately impact platelet aggregation and thrombus development downstream. That concludes this Back to the Basics YouTube video on primary hemostasis and antiplatelet drugs. Check out our other videos on our YouTube channel and follow us on Twitter at @AtriumRx.